We are diving into what might be the most significant technical report for multimodal AI this year, the Qwen3-Omni technical report.
It's a big one, and it makes this one incredibly ambitious claim.
Right. The core idea is that Qwen3-Omni is the first single model to hit state-of-the-art performance across text, image, audio, and video.
Without any performance drop compared to models of the same size that only do one of those things.
And that phrase, without degradation, that's everything. For you as a researcher, this basically resolves that persistent trade-off we've been fighting for years. You don't have to sacrifice text skill to get vision skill anymore.
And the most immediate, head-turning result, the audio performance, it is just incredible. They hit open source SOTA on 32 out of 36 audio and audiovisual benchmarks.
We're talking outperforming major closed source systems, right? Like Gemini 2.5 Pro, even GPT-4o transcribe on some things.
Absolutely. And this is all supported by a new architecture, a unified thinker-talker system where both parts are now a mixture of experts, or MOE model.
And it's fast.
Incredibly fast. They're talking about a theoretical end-to-end first packet latency of 234 milliseconds. That's well under a quarter of a second. Fast enough for genuine real-time conversation.
Okay, let's unpack that central promise first. Solving the multimodal trade-off. We, as humans, we integrate our senses without even thinking about it. Why has that been so hard for these LLM-based systems?
Well, the challenge is really about optimizing a single shared space for data that looks completely different. You have pixel arrays for images, text tokens, sound waves. They're just fundamentally different structures.
And when you try to force them all together, something usually breaks?
Exactly. Historically, if you inject a ton of visual data into a model that's great at text, its language experts kind of get distracted. They're forced to generalize in a way that just dulls their sharp, specialized text skills.
It's like trying to be a top neurosurgeon and a concert pianist at the same time. One of those skills is probably going to suffer.
A perfect analogy. And Qwen3-Omni's big claim is that this sacrifice is no longer necessary. They say they've achieved true parity, and they have the evidence to back it up.
What's the proof?
Their base model, the 30B1, performs on par with the Qwen series single-modal base models for text and for vision, all while adding this new exceptional audio and audiovisual understanding.
So how did they do it? Was it just throwing more data at the problem?
Data was part of it, of course, but the strategy was the real key. They found that mixing unimodal and cross-modal data very early in the text retraining stage was essential.
So they didn't just bolt on the other senses later. They built it in from the model's infancy.
Exactly. It's a fundamental alignment from the start. They also specifically avoided that common approach of, training new encoders on top of a frozen LLM.
Right. Why is that approach a problem?
Because when the LLM is frozen, the new encoder often has to compensate for its weaknesses or blind spots. It ends up sort of massaging the data into the right format instead of just giving a pure high-quality perception. By integrating the training early, they ensured the perception layers were just optimized for raw input quality.
So you get the best of both worlds. Performance that can match a specialized model.
And the ability to do this really novel cross-modal reasoning, like in a video where what you hear and what you see are deeply connected and you need to understand both to get what's going on.
That is a huge advantage over those old cascaded pipelines.
Oh, absolutely. I mean, instead of one model for audio transcription, a second for image analysis, and a third to generate a response, you just have one integrated system.
Okay, speaking of integration, let's get into that architecture, the thinker-talker system. Both components are MOE models now. What's the main benefit there?
It's mostly about engineering efficiency, especially for deployment and real-time use. MOE allows for much higher concurrency and just delivers faster inference because you're not activating the entire model for every single token.
So the thinker is the language core, right? It does the heavy lifting, the reasoning across all four modalities.
Right.
But the really interesting part, I think, is the decoupling of the talker. Can you break that down for us?
Yeah, this is really clever. So the talker's job is to create the speech. In this model, it's decoupled from the thinker's final text output. The talker conditions only on the raw audio and visual multimodal features. It doesn't even see the thinker's high-level text.
Wait, so the thinker decides what to say, and the talker independently decides how to say it based on the sensory input.
Precisely. Think of the thinker as the CEO who sets the message. The talker is the comms director handling the delivery. This lets you use separate system prompts. One to control the thinker's personality, make it formal or witty, and a totally different one to control the talker's audio style, the voice, the emotion.
That's an incredible level of fine-grained control. And to feed this whole system, they rebuilt the audio input from scratch. They swapped out the whisper encoder for their own thing, the audio transformer, or AT. Why move away from whisper?
To get that state-of-the-art performance, they needed to specialize. The IUT encoder is a purpose-built system, trained from scratch on, get this, 20 million hours of supervised audio.
20 million hours. That is just a staggering amount of data.
So what makes this AUT system faster?
It's all about how it processes the audio stream.
Yeah.
It uses something called blockwise window attention, which allows for real-time pre-fill caching.
So it's like a smart scrolling buffer.
Kind of. Instead of waiting for a big chunk of audio, it processes these small fixed-time windows. It operates at a token rate of 12.5 hertz, which means it processes one audio frame every 80 milliseconds. That gives you the precision you need for real-time apps.
That 80 millisecond precision is a massive step up. Okay, so if they can handle all these inputs, how do they keep everything aligned over time, especially in a long video? That brings us to another major innovation here. It's called time-aligned multimodal rotary position embedding, or TMROP.
TMROP, okay.
The whole point is to model those long-range dependencies, the relationship between events in a long video clip. And they do it by basically injecting absolute time information directly into the positional embedding itself.
How does that work mechanically? Do they split the embedding up?
Yeah, they factorize it. They take the standard rotary position embedding and break it down into 3 dimensions, temporal, height, and width. And they reallocate the rotary angles to put more emphasis on time.
Which means for the user that this system can handle inputs of basically any duration. That's a huge deal. The older versions, like Qwen3-Omni, had to chop everything into these awkward 2-second chunks.
Exactly. Qwen3-Omni just bypasses that entirely. It directly aligns everything using temporal IDs that are anchored to absolute time. It's an engineering leap that lets them do high-quality speech recognition on audio that's over 40 minutes long. Think about transcribing an entire lecture in one go.
And they deliberately trained for this, right? I saw in the final stage they pushed the max token length up to over 32,000.
Yeah, it's a commitment to handling real-world complexity. You can't process the real world if your context window is capped at a few thousand tokens.
Let's circle back to that speed. The 234 millisecond theoretical latency latency. That's the difference between a tool and a conversation partner. How do they actually achieve that?
It's a combination of the architecture and the operations. Mostly chunked pre-filling, working in synergy with the MoE system. The thinker and talker work asynchronously.
So they don't wait for each other?
Nope. As the thinker finishes processing one chunk and generates output tokens, those representations immediately pre-fill the talker's current chunk. While that's happening, the thinker's already working on the next chunk. It's fully parallel.
And the MoE structure helps by reducing the I/O load from the KV cache, especially on those long sequences.
Exactly.
Okay, so inside the talker itself, how does it synthesize the waveforms so fast? They mention a multi-codebook autoregressive scheme.
Right, the sequence is really optimized for speed. First, the talker generates just the initial 0th codebook. Then, a tiny little component called the multi-token prediction module, or MTP, generates all the remaining codebooks for that frame.
And that MTP module is super lightweight, right? Only 80 million parameters.
Ultra lightweight. And the final step, the code-to-wave module, uses a lightweight causal ConvNet instead of a slower diffusion model. This whole pipeline lets them start streaming from the very first codec frame. That's how they hit that 234 millisecond target.
And it holds up under pressure. They mention the real-time factor, the RTF, stays below 1, even with 6 concurrent streams.
Right, an RTF of 0.66 means it's generating audio about 1.5 times faster than real time. That's crucial for avoiding lag under heavy server load. This is a system built to be deployed, not just a research paper.
So let's look at the benchmarks and confirm that non-degradation promise. Starting with audio, we know it's good at ASR, but what about more complex tasks?
The dominance goes way beyond just transcription. They got SOTA on music understanding benchmarks, and they significantly beat generalist models like Gemini 2.5 Pro on things like genre identification.
Right.
The model doesn't just hear speech. It actually seems to understand the structure of complex audio.
And for reasoning.
The thinking model variant scored a very high 88.8 on VoiceBench and beat its competitors on the MMAU audio reasoning benchmark.
Yeah.
Shows true audio competence.
Okay, now for the big one, text. Did they maintain performance there?
They did. In fact, the Qwen3-Omni instruct model actually beats the much, much larger Qwen3-235B non-thinking model and even GPT-4o on some complex reasoning tasks like AME25. So the core language skills were absolutely preserved, maybe even enhanced.
Diffusion.
Comparable performance to their dedicated vision model, Qwen 2.5 VL. And it really excelled on math and STEM tasks against closed-source competitors. But the place it really shines is audiovisual.
Right, where it all comes together.
Exactly. It hit SOTA on the WorldSense benchmark and showed big gains on complex reasoning tasks like video homes, which are tasks that absolutely require connecting what's happening visually with the soundscape. That's the real payoff of this end-to-end integration.
We should also quickly mention the localization here. It's impressive. 119 languages for text, 19 for speech understanding, 10 for speech generation.
That's a huge scope. And the speech quality is top tier. They show competitive zero-shot TTS, and they use RL to make it more stable and realistic.
They're even claiming superiority over established players like 11 Labs and multilingual speech generation. And that cross-lingual voice, cloning a voice in one language and having it speak in another is just a powerful demonstration of control.
And one last thing, we have to mention the captioner variant. They saw a gap in the market for a general-purpose audio captioning model.
Right. This version is fine-tuned to create these detailed, low hallucination descriptions for any kind of audio. Not just speech, but sound effects, music, mixed environments. That tool alone seems incredibly valuable for accessibility and media analysis.
So if we step back, what's the big picture here for you, the engineer or researcher listening to this?
Well, the core takeaway is that they've provided really strong evidence that you can do fully integrated end-to-end multimodal training without killing your core unimodal stills. This gives you huge advantages over those fragile, expensive cascaded pipelines.
You get stronger cross-modal reasoning.
That critical 234 millisecond low latency and just lower system complexity and cost because you're only deploying a single model.
It feels like a philosophical shift,
Yes.
moving away from hyperspecialization and back towards a more robust general-purpose integration. But they did mention a limitation. The current model still struggles on ultra-long video benchmarks.
Right, due to constraints on positional extrapolation.
Which leaves us with a really interesting question for future work. If TMROP was the key that unlocked 40 minutes of audio context, what's the next step? What new positional encoding or maybe some kind of dynamic chunking strategy is needed to unlock multi-hour, ultra-long form processing?
We're talking about processing entire movies or days of security footage, tackling challenges like multi-speaker ASR, and maybe even audiovisual proactive learning. That seems to be the next frontier.